just gonna check my email this morning.
Yeah, as far as
like when you were sending out the notification for
announcements,
formulas,
yeah,
that was popping up, so I would get those. But when you sent that email,
when you go to Canvas and you go to Settings, there's a tab that says Notifications on it, and when you click on that, you can set up your email. You can add another email. You can add a cell phone. And you can say on them how often you want to be, like, let's say for your Yahoo account, you want to be notified right away. Your alamo.edu, you want it at the end of the day. Your cell phone, you want to text right then when it happens. And you can do that for discussion postings, communications, whatever. I put a little video showing how to do all that.
Yeah, and I did that, but
yeah?
I don't know what happened. I just never got the one for the email.
And you never got it at all? You still haven't gotten it?
Well, I got it, but I never got the notification.
Okay. Yeah, you know what I've noticed with Canvas is that things are delayed. Like I'm getting stuff, like I'll send out an email or something and I'll get the notification, but then it doesn't appear in my inbox till later or the other way around. So I don't know what's going on with it.
Because I was receiving your notifications about that you sent out the I guess what is it?
Formula sheets, yeah.
And then the modified formula.
What I'll do from now on is when I send an email out, well, I don't want to fill your all the announcements up, but I might have to send an announcement that I sent an email. Or just, check your inbox more often. I don't know, yeah. I'm sorry.
I would just text message everybody. I like that.
Yeah, you want me to text everyone?
Yeah.
Give me your address. I'll just bring anything that I have for you. I'll just drop it off at your house. Is that okay?
You can send it through priority mail. Just make sure put your beer on.
Okay, so let's talk a little bit. I was kind of sick for the first half of the weekend, but then I kind of started feeling a little better. So Saturday and yesterday, I started doing homework. The homework problems from 5.5, 6.1, 6.2, and 6.3. Just because I haven't taught this class in like 5 years, so it's, I just want to do the problems again and just get a feel for what you all are going to have to be going through. So this is what I did. This is my homework for over the weekend. And I was sitting there and I was thinking to myself, and I came this close to sending an announcement to everyone. It was, I think, Saturday night, and I was tired. I'd been doing this for like 3 or 4 hours straight. And I was just thinking, man, I know how to do this. Like, I know this, right? And it was still just, it was just so much work. And there's just so much in this material that I just wanted to start class off by letting you know that it's time to drop the class now. that if you've never seen integration before, you've never seen antiderivatives and all the techniques, if you haven't been exposed to it yet, you're going to go to places in your math that you have never gone before. Like you are going to be taken to a level that you might sit there at the end and be like, wow, I didn't know I was capable of that. Like I didn't realize that math actually required this much work. So it's going to be a huge step for you, and I want you to be ready to face that. All right, so the amount of work that you are going to have to do outside of this class to do well in this class is significant. I mean, if it took me a good 6 hours to put together 3 sections of work, it should take you 6 hours per section. I mean, it's a lot of work to do these problems. So, be ready for that challenge. You can do it, but you got to be ready to put in the effort, all right? And then in doing all the problems, I realized, man, there's just so much stuff that you have to call upon from your past math classes. So the back of the book has 6 pages, 6 reference pages. And this is now the official formula sheet. I sent it out. I put an announcement for it. If you want a hard copy, who wants a hard copy? I have a hard copy. Okay, so I'm just going to pass this out. This is the official, what you can have on the tests for every test, every quiz we have in this class, all right? And so my advice would be to have this next to you while you're doing your homework. What's that? Weird. Is that the only one? Make sure you have 3 pages. So my advice would be to sit with this while you do your homework. And no extras. Can you all pass those over? Any extras back there? Just get them around there.
Is it okay to write on them? Like our notes?
Well, here's the thing. I don't want you to write on these because I will tell you what you're allowed to have and what you're not allowed to have. So if you start adding a bunch of stuff to this, then I could look at that as having an unfair advantage over someone else in the class on a test. So don't touch these. If you can have something else, you want to start putting other formulas somewhere else, put them on a separate sheet, okay? So be aware of what's here, all right? One good thing that this sheet has that we'll be calling on today is the reference sheet 5, sorry. Reference page 5 has the derivatives, common derivatives, and then reference page 6 has common table of integrals. And the book, your book actually has more reference pages. I think they have like 100-something formulas. These are the only 20 you're allowed to use. These are the only 20 right here on a test, okay? So, I mean, when I did all this work, I mean, I was really, it was fun, I mean, because I enjoy this, but I really want to make sure that you're seeking help if you need it, and that you're, getting together. You really should try and get a group of students together. Don't wait till like the day before the test. Form a group now, get together, work out problems, maybe divide and conquer. That's what I used to do when I was a student. We would divvy up the problems. If you have 40 problem set, we had 5 people in the group. We'd each do a few, get them, master them, bring it to the group, and show everyone else how to do those problems. And then you just share, and that way, whatever you want to do, but I mean, it's on you to do that, all right? I made the complete solutions for the even problems, right, from 5.5 to substitution. That's what we're going to do today. All the even problems I worked out by hand. They are on where our class videos are. They're in there. I just put them in there this morning. It's me talking through my solutions to every even problem. All right? It's a 40-something minute video. So if you want to look at 5.5, look at any of the problems from the evens and see how to work them out, go watch the video and I work through them. All right? The odds are your homework for 5.5. And I'm going to work selected odd problems today. All right? My advice to you, work through all the odds. When you're done, work through all the evens. Any questions? I know I had one homework question. Is there anything else on homework? All right, I'm ready to start if there are no questions. This stuff, I already said, I feel like a broken record. This stuff builds on itself, and it builds on itself very quickly. So the stuff that we learned about antiderivatives and power rule, right, x to the n and all that, I'm assuming you've mastered that at this point. And now we move into substitution. When we come in next class, I expect that you have mastered the substitution, which is a lot to expect, but be ready. This is a marathon, but it's a sprint marathon. It means you're sprinting the whole way, all right? All right, I was asked about, which one was that? 8? Okay. Please pay attention to a couple of things that I do today. My notation, all right? The way I write things, how clean things are. These are things I'm going to be looking for in your work. You may do horrible math, but if it's clean, I'm going to take off less than if it's horrible math and I can't tell what it says either, So let's work on neatness and making sense. The problem is presented as the integral x squared e to the x cubed dx. That's the problem. Now, we are in the section called substitution. So let's briefly talk about the things that are involved with substitution. With substitution, here's what we want to be paying attention to. Number one, we're looking for something and its derivative. Right? That's the whole idea of substitution. Look for something within the integrand and see if you can see its derivative there also. And once you've done that, you replace the something that you just found with u. Now, depending on your problem, you might use a different variable. So like, for example, if the problem has u's in it, you don't want to replace it with u, you would use v or w or something else, right? But in general, we'll be using a u in the class. Here's something important. You never will replace u equals x. You'll never have a problem like this and say, oh, the substitution I'm going to make is let all my x's be u's. Because all that's going to do is rewrite the problem in terms of u. So you'll never, ever do this, all right? The next thing you want to do is, after you've done that, is find du, and that will be equal to the derivative of that something, right? The derivative of that something dx. I'm going to work through an example so you'll see all this come out. Here's the thing to be careful with. Okay, careful. The du that you get here, the du is the derivative of the something, right? And we were hoping that that derivative of that something appeared somewhere in here, didn't we? Like we were saying, I saw something and its derivative. That thing that appears, that du that appears, you need to make sure that that du is not in the denominator, not under a root, etc. You don't want your du to be trapped inside of another function. You want it to be sitting there by itself. And you'll see this again as we move through some problems, all right? All right, so let's go through this now. Do we see something and its derivative? X cubed. The derivative of x cubed is 3x squared. So that's the something and its derivative, right? Well, we said x cubed and 3x squared, right? We don't have 3x squared, we have x squared. We're off by a constant, right? It's okay to be off by a constant. In general, anytime we're off by a constant, we don't care, because we'll be able to fix it. So if you want to, you could add to this list, it's okay to be off by a constant. All right, so here I'm going to choose my u to be what? X cubed. Okay, so here, look for something as derivative, replaces something with u, find du. The du will be du equals 3x squared dx. And remember in class last time I said the dx came from the dx being down here, but I brought it up to the other side, right? All right. Now, here's where I have to take this and rewrite the integral. So watch what I do here. Equals. Equals means I'm telling you this is the same as this. Watch. E to the x cubed x squared dx. Y'all agree that's the same problem? All I did was just move that x squared over here, right? Now, I have x squared dx here. I'm going to underline it. I have x squared dx here, right? But I have this 3 here, which I don't want. Like, it's not there. I don't want it here. So to get rid of the 3 here, what can I do?
Put it in front of 3.
Divide by 3.
Divide both sides of this equation by 3. Or multiply both sides by 1/3. Now, there are different ways to teach substitution. So I know for those of you who have seen this before, if you're comfortable with a certain way, stick with it. But this is the way I teach it. So I multiply both sides of this equation by 1/3. And so now what I've done is I've I've kind of massaged this to make it look like the piece that's in here. So now I have an exact match. This and this. With me? Questions? Okay, this piece up here, x cubed, is what in my problem? That's my u, right? And right here, this piece is my 1/3 du. Yes? So now this integral becomes, so I'm going to use an arrow now instead of an equals, only because I've changed the variable over, all right? This is going to be this. It's going to become this new integral in terms of u instead of x. So I write e to the u times, because that's multiplication, x squared dx is what? 1/3 du. So I put my 1/3 here, du. And we said last class that constants can come outside. So 1/3 integral e to the u du. And now I go to my formula sheet that I handed you. And there should be a formula on reference page 6. Formula number what? Formula number 4. And on, you know, I said I did a video of my solutions. Every time I used a formula, I put it like this. I'm running out of room here, so I'll put it up here. I put equals, and then above it, I put like the formula I used, like 4, right, to go from here to here. So I have the 1/3. The antiderivative of e to the u, according to this thing, is e to the u plus a constant. But we're not done, right? We're not done. What is u? U is x cubed plus my constant, right? Sorry, I'm kind of did this here. Now I'm done. Yes?
On the d of x, things like that, when you're pulling the d of u and d of x,
Yes.
sometimes I actually do leave that out. Is that going to be a problem?
When you leave what out?
I leave out the dx.
Yes, don't leave the dx out. Yep, don't leave it out. It'll come back to haunt you later. Yeah, you might get away with it for a little while here, but it'll come back to haunt you. So. Yeah, so this is it. So watch, here's how I'm going to write my final answer. Okay, watch this. I mean, that is it. I could box it, but here's what I'm going to write. 3 dots, triangle, like this in math means therefore. Okay, that means therefore. So here's where I am. Therefore, I'm going to rewrite the entire problem. X squared e to the x cubed dx equals my answer 1/3 e to the x cubed plus c. So the things I'm going to be looking for when I'm looking at your quizzes or homework or exams or whatever it is that I would be grading is for just the cleanliness of the problem. Can I see easily your substitution? Does all of this look good, and can I make sense out of it, right? Because if you don't show me a bunch of stuff and you just get an answer, it's wrong. It's all wrong. If you make substitutions, but okay, maybe you forgot to do this step, I can maybe pick that up when I see it and give you something for it, right? All right, that's it. That's probably the cleanest substitution we're going to see. It doesn't get any easier than that sort of substitution. It was almost identical. It was almost u du, almost just off by 1/3. We talked about Leonardo DiCaprio, right?
No.
We didn't talk about Leonardo DiCaprio in here?
Try not to. I would have remembered that.
Okay. Well, you remember that scene in that movie Titanic, right? At the very end, where he dies. Is that why you love that scene? The scene where he's sitting there, right, and he's just kind of like holding on to that lady's name? Rose, right? Rose. He's a big fan over there, right? This movie, Titanic, a little Titanic tattoo or something. Anyways, you know how he's like sitting there, he just slowly kind of fades into the abyss of the cold, dark sea? All right. I want to make sure when I'm looking out here that I don't see any of you, if you feel like Leonardo DiCaprio is, at some point you've got to say something, all right? You gotta stop me or come talk to me. I don't want you to have that slow death. All right, I'm doing number 11. So I'm doing selected odd problems here.
Is that 5.3?
I'm in 5.5. Now, until you become a master, you should probably show as much detail as possible. I'm sorry?
She answered my question.
Okay. So find the antiderivative of this. I'm looking for something in its derivative. Do you see it? What's the something and what's its derivative? Natural log of x. And what's the derivative of natural log of x? I don't see a 1 over x. You see a 1 over x?
Yeah.
You see it? Okay, so maybe you need to do this. Maybe you need to do this instead to see it. Just peel that thing apart, pull that x that's down here off to the side as its own little fraction. Now do you see it a little cleaner now? You see the natural log of x squared times 1 over x. There's the derivative of natural log. So it's there, right? Something in its derivative. So let's try that. Let's try our substitution. U equals what? Natural log of x. Du is 1 over x dx, right? And don't forget that dx is always going to be there. And holy look at that. That's exactly what I have, don't I? I have exactly 1 over x dx. I don't even have to adjust that. That's ready to roll right there. And I have my u right here, don't I? So how could I rewrite this integral then? So I'm going to have an arrow now, kind of letting you know I'm switching it now to a different variable. So natural log of x is my u, right? So u squared. And then this whole thing is just my du, isn't it? Is that all right? And that's a formula, isn't it? Power rule. Formula number 2. Right? Formula number 2. We have something to a power. So by formula number 2, this becomes 1 over n plus 1. So 1 over 3 u to the third plus constant. Using formula 2, back, right there.
Oh, okay. Hold it out already, the 1/3.
This is 1 over n plus 1. Yeah, this is 1 over n plus 1, u to the n plus 1. Is that good? Sure. Are we done though? What do we need? What's u? U is natural log x. So I think what I'm going to do is this now. Just to save us a little bit of time. I'm going to go straight to my therefore now. Therefore, my original integral, natural log of x, x squared over x dx, is equal to 1/3 natural log x cubed plus c. Yeah, the 3 dots here like this is therefore. So far, the 2 problems we've had, our substitutions were pretty clean, right? Not a whole lot of stuff happened when we did them, right? It was pretty straightforward. So let's look at another one now. How about 15? 15 just looks intimidating. Integral a plus bx squared over square root 3ax plus bx cubed dx. And I'll share something. This is honestly the truth, okay? So you know. Like I said, I haven't taught this class in probably 5 years. I did all of the even problems this weekend for like, you know, 5-5, 6-1, 6-2, 6-3. And it took forever. I didn't touch the odds because I was hoping I'd come into class and do the odds. So I haven't worked this problem. I have no idea. You know what I'm saying? I'm hoping that I get a little bit tripped up at some point today. I'm hoping that happens so that you can see what it's like to get stuck a little bit and how if you get stuck, you got to keep going. You know, you got to try something else. So let's see. I'm excited about this. First of all, what about A and B in here?
It's constant.
They're constant. Now, that's important because in these problems, anytime you see like A's, B's, C's, D's, alphas, betas, a lot of times those are constants. The things that they reserve as variables, X, Y, Z, beta, right? And I believe in the front of the book, somewhere in the front, the author actually says what they use for variables most often. So if you want, you can reference that. But in this problem, how can we tell what the variable is? Dx. Dx actually tells us kind of like with respect to what variable here. So X is our variable, A and B are just numbers. They're fixed numbers, we don't know what they are. Okay? Something and its derivative. Yeah, so if you look at the entire numerator, right, would you agree that this is a quadratic expression? Yes. Quadratic? The denominator inside the root, this is cubic, isn't it? What's the derivative of a cubic, third degree polynomial? It's squared, right? It should be a second degree polynomial. So I have third degree here, second degree there. So if I choose this as my u, when I take this derivative, I've got a squared. So that's a good place to start, probably, right? Try the u equals, now let's go for the whole thing. Let's go for 3ax plus bx squared, x cubed, sorry. Let's just choose the whole thing and see if it works. What's du? 3a, because derivative of 3ax is 3a, plus 3bx squared. And what do I have? dx. And technically, we should wrap these two terms in parentheses like that. Is that what we have up there? Is that what's up top? So even though I don't need to do this, I'm going to do it just to help some people who might have problems seeing this right now. I'm going to take that numerator and I'm going to peel it off to the side. Like that. Do you agree? Take that, push it out here, there's a 1 up there, and I've got this right here. Now, do we have this and this matching? Not quite, right? What do we need to do here?
Divide by 1/3.
Yeah, look, there's a 3. If I can factor that 3 out of both of these, I have the a plus bx squared, which is up there. So again, multiply both sides by 1/3, and this works. Did you say easy? Yes? It's good if this is feeling easy to you. I'm hoping it. No? Okay. Ask a question though. Okay, you gotta let me know what part you're not getting so I can help you. Can I keep going? All right. So this matches, doesn't it? This guy right here matches this. And then this part, just what's underneath that radical, right? That matches this. So what would my new integral, I'm going to put the arrow here for my new integral, what would my new integral look like?
1/3 of u over square root of u.
Okay, I'm going to do it this way. 1 over square root of u times, this whole thing is 1/3 du. And now, yes or no? Yeah. Now what can I do?
Pull the constant out.
Pull the constant out. And then I need the antiderivative of this at some point, right? So I'm going to rewrite this using powers. So this is equal to 1/3 came out, integral u to what power? -1/2 du. So square root means u to the 1/2. Bringing it up into the numerator means changing the exponent to a negative exponent. And now that's a u to the n. So I can use what formula? The second one? That's 1/3 times. So honestly, I know this is a stretch. Here's where I expect that you would be at this point. After all the homework you did over power rule, that you would say mentally, I know this is going to be 1 over n plus 1. N here is -1/2. -1/2 plus 1 is 1/2. 1 over 1/2 is 2. 2. U to the 1/2, which is the same as square root of u. So that, I mean, now if you need to work a little more of this in detail, you can. But when I say it builds on itself, that's the rate at which it builds on itself. Like last class, now that's what we do instead of a bunch of other stuff. And then what else? Plessy. Therefore, my final answer, the integral, you don't have to rewrite the whole problem every time. I'm just kind of doing it because, you know, why not? We're not worried about running out of ink or anything. So that equals 2/3 square root of, what was my u? That was so long ago. 3ax plus bx cubed, then plus my c. So there it is. Yes?
Do you care if I just let the improve this easy? It's a 1/2 power, or does it have to be improved?
You could have put it as a 1/2 power. That's fine. Everyone, he's saying, could I have left that as u to the 1/2? Yes. As long as you know that u to the 1/2 is the square root. As long as you know that, we're good. So how do you feel? Are you just cold? You going to be able to get, the rescue boat going to be able to get to you? Or you going to be okay? Now I chose to do this problem today because not everyone in here has experience with these hyperbolic trig functions. You may not have seen those in a previous class. And I don't expect you to have a deep understanding of the hyperbolic trig functions. What I do expect for you to know is what the derivatives of the hyperbolic trig functions are. So if you could, go to your reference page, I believe it's 5. We'll have derivatives, and I'm hoping it has the hyperbolics on here. So if you look on reference page 5, formulas 25 through 30, it has all the derivatives of the hyperbolic trig functions. And what do you know? The derivative of the hyperbolic sine function is the hyperbolic cosine function, isn't it? So I have right here the hyperbolic sine being squared, then times the hyperbolic cosine. So what should I choose as my u? I'm going to do it two ways, just to show you the difference. If I choose it to be the hyperbolic sine, then what's du? Cosine hyperbolic x dx, right? Do y'all see that? Yes? Let's compare that to doing it the other way, because I heard some other people say, well, I could do the cosine hyperbolic, right? Yeah? What's the derivative of cosine hyperbolic? Sine hyperbolic. Dx. Now, which one is right, or do they both work?
Actually, cosine, using sine is the only that work.
Let's see what rewriting this integral here would look like. The integral would become, well, my sine hyperbolic, right? Right there, that's my u. So it would become what? U squared. And then cosine hyperbolic x dx is exactly cosine hyperbolic x dx, which would become du. And that's a power rule, isn't it? If you do it the other way, then the cosine hyperbolic x, right? The cosine hyperbolic x is just this piece right here, isn't it? That's so it would become a u there. But what is the sine hyperbolic x right here? And then the dx, that doesn't really match, does it? Because this is squared. So isn't your du messing around with something that's squared? Isn't your du kind of inside of something complicated here? That's what I was putting down on my notes. What did I put on the board in the beginning of the class? You want your du, it can't be in the denominator, it can't be in a root, right? Etc. You don't want your du to be stuck in something complicated. Here, complicated is the squared. You see? You have to avoid that at all costs. So in this problem, this is not the approach. The approach is this one. In fact, you wouldn't be able to do it this way. All right?
Can you show me how you did the other side? I was writing down.
Okay. Well, I just realized that this is something, sine hyperbolic is my u. The derivative sine hyperbolic, because of the formula sheet, is cosine hyperbolic. And then this right here, cosine hyperbolic x dx is this piece, that's du. And then this sine hyperbolic is my u, and then it's squared, so that becomes u squared. You sure? Okay. And then from here, what's the answer? 1/3 u cubed. But what's u? Sine hyperbolic, so sine hyperbolic x cubed plus c. So I already went and did the 1/3 u cubed and replaced the u with sine hyperbolic x. Yes?
I don't see where you got the 1/3 from.
Power rule on this. See, I don't have the integral anymore. So going from here to next step, I use formula 2 for integration.
Okay, I see.
Anyone else have a question on that? Uh, 25. If you feel like, hey man, he's taking away all the good problems, like I wanted to do some of these on my own. Trust me, you have plenty of work in this section if you need practice. So I made those solutions to the evens, right? The idea would be that you go to the even problems and you do them. You try them. And if you get stuck, you know, you try, and if you really get stuck, you go look at my answer, and you at least see what my substitution was, and then just write that down and try it yourself. Eventually, if you need to watch my whole thing, you can. All right? But there's no excuse like, I just couldn't figure out how to do those. Anybody have the solution manual for this book? Nobody has the solution manual for the book? Wow.
I haven't looked for it yet.
I'm surprised. The student solution manual? I'm about to get the complete solution manual, but that has even and odd. Most students have the odd one. I'm just surprised. Because the solution manual has like detailed solutions to all the odds.
Yeah.
And they leave out some steps, but wow. Maybe a couple of y'all can pitch in and get one or something. All right, back to this. What do we got going on here? Yeah, that's a bad thing. Sorry. My mistake.
That's the first clue that sums it up.
How do you want to rewrite it?
1 over the
You want me to rewrite this as 1 over the square root of 1 minus x squared times sine down here? Or like a separate fraction?
No, times 1 over sine.
Down here?
Dx over 1.
You want me to do this? Another fraction or under here? Another fraction. Like this?
Times
Like this? Why?
Can't you just make these things? Can't you just go negative 1/2? First one?
You mean like move that up to the top and make it to the negative? Sure, you could do that. Would you want to though?
First off, you want to see like all the parts that you have.
You're looking for something and its derivative, aren't you?
Our sine and its derivative would be this.
So if you go to reference page 5 and you look at number 19, the derivative of arc sine is 1 over the square root of 1 minus x squared, which is exactly what you have right there. So do you see what I'm saying? Like your knowledge of this existing and connecting it to all this is very important in this class. Now you'll get to a point eventually where you just know the derivative of arc sine is you just know it. Arc cosine, you know it. But it just takes a little time. So u equals what? Arc sine. Sine inverse of x. Du is 1 over square root 1 minus x squared dx, which we've got right there. Now, if I were to do this problem, in fact, I'm going to do it. Just because I'm being pretty meticulous with detail right now, so I may as well go one more step. I only did that so you could see that this whole piece is this, and then be careful over here. The sine inverse of x is my u, right? And are we all clear and understand that sine inverse x, this little -1, is not a power? It's not like raised to the -1. It's one of those crazy things with notation where we use the same thing to mean two different things. So this is the inverse sine function, not raising it to the -1 power. So you don't bring that up and make it sine, right? All right, well, if that looks like it's straight off, right? I mean, this is exactly what we have, so that's a du straight up, nothing was off. We've got the sine inverse x, that's my u, so what's the integral become? Integral 1 over u du. Now I could bring that u up and make it u to the -1, couldn't I? But formula 3, right? Formula 3, since this means the same thing, right? 1 over u du is the same as du over u. Formula 3 tells me it's what? ln u plus c, or actually ln absolute value u plus c. And what's the u in this problem? Arc sine of x. Therefore, the answer is natural log absolute value arc sine of x plus c. How do y'all feel? Come on, give me some feedback. What are you thinking right now?
I'm having trouble coming up with the whenever you say to look for something in its derivative. I have trouble finding it. After I see you do it, I'm like, okay, that's
Yeah.
And then just right off the bat, I can't.
I know, and it's gonna continue to be a challenge, and the only way to do it, honestly, is to sit with the problem and try different u's. And also, the more knowledge you have of derivatives, the easier it will be to go backwards. So, that's why I've said before, like, if you were in Cal 1, if you were exposed to the derivative of arcsine enough, you kind of already have this connection when you look at it. If you don't, it's going to take some time to build it up. But you have to take swings at this. You try U, if it doesn't work, it doesn't work. If it does, it should all kind of just paste together nicely. If it doesn't, then try something else. Yeah, I know. Let me see if I can find one. Oh, I like the next one. Oh, I really like the next one. Secant cubed x tangent x dx. Yeah, this one's good. You're looking for something in its derivative.
First, you want to break down the secant cube to whatever secant cube equals, which is the derivative of tangent.
Are you saying you want to take everything in terms of sine and cosine?
I'm trying to figure that out because I don't.
That's always an option, okay? Anytime you have trig stuff,
Yeah.
you can always try and go into sines and cosines. I agree. I'm not there yet. I want to see if anyone can see something in its derivative.
Yeah, that's what I was trying to figure out.
Can someone get the door over there?
Because then you have the derivative of tan x is secant squared.
Because
All right.
not all trig functions.
Let's do this. How many things does it look like we even have a possibility as choosing for you?
Two things.
What two things?
Secant cube and tan x.
Well, you don't have to pick the cube, though.
But secant.
You could go secant, or you could do tangent, right? So,
But then when you pick tan, then your du would be secant cube dx, and then you said you don't want nothing like that, right?
well, but the derivative of tangent is secant squared x.
Yeah.
So let me just real quick. I'm just thinking through, like, what is it that I would choose? If I use secant x, that's one option. Here's my other option, choosing u to be tangent x. So let me look at the derivatives of each of these. Derivative of secant x is secant x tangent x dx, right? What's the derivative of tangent x? Secant squared x dx. Okay, let's look at the second one, because the second one's not going to work. All right, so let me get this one out of here real quick. If I use u as tangent x, if this was secant squared, we'd be done, wouldn't we? Because we'd have secant squared and we'd be in business. You see that? But it's cubed, so I can't do that. So if I did this sort of thing, even though I could peel this off, I could write this integral as secant x tangent x secant squared x dx. Do y'all see that's the original problem? This piece right here is my du, isn't it? Right here? Yes? This piece right here is u. So I'm all happy, right?
Yeah.
But then I got this secant x sitting here still. And I can't do anything with this, right? There's nothing I'm going to be able to put into that place. So I'm going to have a secant x u du, and so I've got x's and u's mixed together, and I can't have it. So that looks like it may not work, right? Now if I go here and rewrite the problem, let me see how I can rewrite it so that I get this to appear. How can I rewrite this? How about secant squared x secant x tangent x dx? Isn't that the same problem? Secant cubed, that's it. I just peeled one off. And so I see here secant x tangent x dx is secant x tangent x dx. That's my du. And this is what? U squared.
So you have to watch out for that sometimes because not all the trig functions times themselves like multiply out to what you think they are. So you have to know like when they multiply out like that.
Yeah, we are at the tip of the iceberg, okay?
That's why I know you have to be careful by like doing that because depending on how you do it,
Yeah, I mean, there's going to be problems. There are going to be problems where we're going to take this secant squared x and we're going to use the Pythagorean identity to change it to 1 plus tangent squared x. And I mean, there's going to be all sorts of things we're going to have to do and multiply out. I mean,
Yeah, that's why you have to be careful doing that because you don't always know that it'll come out that easy.
yeah. So when I'm looking at this problem, right, when I looked at it, you know, that's what I was thinking mentally is, what do I choose for you? You know, secant or tangent? And it's kind of, for me, a mental thing. If I choose secant, then I need a secant tangent somewhere, because I know the derivative of secant. And so I kind of mentally, you know, say, oh yeah, there's one over here like that, and then, but you got to get to that place, right? If not, you just got to take some swings at it. Yes?
I must have just pulled secant out of secant.
This secant cubed x is the same as secant x times secant x times secant x, isn't it? Yeah. So if you put these back together, that's secant squared. So I just left the secant squared here, and I pulled this secant over here with this one so I could get my du to appear. Can I keep going, or? So what's my integral become now?
Squared du.
So secant x is u squared du. This is 1/3 u cubed plus c, 1/3 secant cubed x plus c. So there's my integral. Power rule. Integral goes away, 1/3 u cubed. Replace u with what u is. You know, the challenging part, one of the challenging parts of this course, there's a lot of things that are challenging, but is that when you are faced with the test, right, you're going to sit there with a problem, and maybe it's not going to be a click right away. And that's what gets a lot of Cal 2 students, is that here's an integral, and you may get that u on the first try and be like, boom, I'm done. Or you may get stuck on it. And so it's hard as an instructor to actually create a test that's truly fair and gauges where you are, because if you get stuck on something, you're stuck, you know? So a lot of times what I'll do is I'll have a problem and it'll have a part A, B, and C. And there will be different levels of difficulty in each one. So if you do an A-type problem, it's like a really hard one. B is like a B-type. C is like a low level. So if you do all the C-types, you can get a C on the test. Does that make sense? Just show like basic skills. You can pass the test. But if you want an A, you got to be able to do the harder stuff. That make sense? So that way you're not completely dead in the water, Leonardo DiCaprio style. You know? Integral sine 2x over 1 plus. Oh, sorry, this is number 31. All right, I've got to stop the video and restart it, so I'm gonna let you look at that for a minute.